Hi everyone, welcome to the first episode of the AstroLaunch podcast. I'm your host Amy, and I'm so excited to introduce you to our guest, Anthony Juan, a flight controls engineer at Robinson Helicopter Company, and talk to him about his journey into the aerospace industry.
Hi, Anthony. Welcome to the podcast. Thank you so much for being here.
Thank you for inviting me onto this. I am a flight test engineer at Robinson Helicopter Company. I'm currently about 3.5 years in Robinson, and most recently, I'm 6 months into this new role as a flight test engineer. Previously, I've spent about 3 years as a structures engineer in the structures department.
What inspired you to pursue a career in aviation?
This started as a kid. I was always into kind of typical boy kid that was into cars, transportation. But if there was one singular event that made me want to pursue aviation, I would say it's 2006 or 2007. My parents and I, with my brother, we went down to Marine Corps Air Station Miramar Air Show, and I was able to see planes fly and do demonstrations. I was able to see them on the ground, and if there was one certain culmination, that was it. That's when I was like, I have a bug. I have a bug for transportation, but I also have a bug for aviation, specifically airplanes. Helicopters came on a little bit later than that, but that's kind of where it all was. So, as a kid, I wanted to be a pilot. Growing up with very traditional Asian parents, pilot was not necessarily the path they wanted me to go. They wanted me to go engineering if I was going to go down that path. And I was like, okay, what is the best? What is the way I can do kind of combine engineering and aviation? And that was obviously aerospace engineer. And I ended up pursuing that. My dad was an electrical engineer, so he was like, "You want to go do that?" Did not understand electrical engineering at all. Didn't really have any passion for it. But I had a passion for aviation. So a lot of time, in high school, I did a lot of applying to aviation specific engineering. Environmental engineering was also something I was really interested in. But I ended up landing a landing. Ended up applying to Embry-Riddle Aeronautical University in Prescott, Arizona, and did my 5 years there. Got my bachelor's with. Technically, my bachelor's was in mechanical engineering, but I also had a minor in aerospace engineering and a minor in alternative energy. So that was where my passion kind of stood from. Ultimately, after that, career fair, landed a job at Robinson, and I've been at Robinson since.
That sounds like me too, because currently, growing up, I was always interested in the space. I would look up in the sky, and all the movies that I would watch with aviation, it would inspire me to do something like that. And say my dad is a mechanical engineer, but right now he works in software, and I don't like that either. So
it's like I think, especially with electrical engineering, it's also just very. It just never made sense to me. I think I took physics 3, which was like electromagnetism and stuff like that. I took it twice, and both times I got a C. I just did not understand it at all. And it's like, okay, well, I know what I don't understand, and I passed the class. I'm just gonna move on to the next thing. So, ended up not also I ended up not understanding aerodynamics that well. I know bits and pieces from it. So that's why I ended up, even though I went into Embry-Riddle with aerospace engineer, I ended up transferring to mechanical engineering. So I ended up doing more thermal mechanics, engine design controls for turbo shafts, turbojet design parameters and stuff like that. Ultimately, I'm not using any of that here at Robinson, but that's kind of what it is. It's college is a basis for how to learn something. So I learned how to learn, and I learned how to study, and that is you do a lot of your learning on the job.
So as for your job, what do you do as a test controls engineer?
As a flight test engineer. So it's not test controls, I guess. But as a flight test engineer, I am the final test of the systems on an aircraft. So whether it be a new engine control system or a new aerodynamic surface, a new main rotor blades, the final real life test is going to have to put it onto an aircraft. In this case, put it onto a helicopter. We are the last stop where all these sub-disciplines, whether it be electrical engineering, system safety, systems integration, structural engineer, design engineers, all this culminates onto the test vehicle itself. In this case, one of our helicopters, and we go and test it, verifying that we have met the FAA certification for Part 27. Part 27 dictates helicopter certification, so all of us we need to follow. It's a very broad certification basis, but there's been so many other helicopters that have gone through it. They have kind of a guideline on how to go about certifying helicopters. So we are the the last stop before certification. A lot of times it's been tested, it's been, strength of it's been certified. How does it do in real life? How does it do on the aircraft? How does it perform on the aircraft? Does a pilot recognize that it's beneficial to the pilot as well? So that is our final step. So it's a lot of it's functional testing, sometimes it's performance metrics if it's a new aerodynamic surface, but it's also support of some of our technical publications, whether it be how to maintain it, how to install it if it's a retrofit kit, but also how to, if such a thing fails, if let's say we have an engine control system, if the engine control system fails, can you still fly the aircraft? Or what is a procedure? Can you disable it by pulling a circuit breaker? Can you disable it by pulling a switch? How does a pilot then respond to that new emergency procedure given a new engine control system?
So after you do all these tests, if something doesn't work correctly, do you take it back to the engineering to fix it?
Yes, usually that's the case. Usually we try to minimize as much of that because it's we're dealing with systems that we kind of understand. But for example, currently in the works is our newest design, the R88 helicopter. It's a clean sheet design with inspirations from our previous designs, but it's inspiration from it. But it's a brand new clean sheet aircraft, so there's going to be a lot of learning curves and teething pains in the initial design process. We didn't consider this until we started putting it on the test vehicle. So especially with the R88, there will be a lot of that feedback. Okay, like we found this issue, let's go put it back to the structures. But we try to deal with it if it's a systems integration issue. That's a lot easier to fix than if it's, oh, I have made this bulkhead way too thin. I've made this tail cone way too thin. It's like, okay, that is a whole nother issue that's going to take a lot more time. So we like to deal with a lot of the structural side beforehand with fatigue testing, with static testing of real life examples to try to catch all of those before it goes onto a test aircraft. Plus, now I can fatigue test on the ground. If it breaks on the ground, it's not an issue because no one's attached to it. It's not. We're mimicking loads. The instant you start putting a person into it, that that increases the safety risk so much. You don't want to put something like, I don't know if it's going to structurally be sound. I don't want the tail cone to fall off mid-flight and we lose not only the aircraft, but we also lose as experienced pilot. So there's a lot of that where we try to minimize as much the risk going into it, not also from both a safety standpoint, but also a design standpoint of like, okay, we have dealt with what we can. Now let's see how it performs in the field. So there is a lot of back and forth. We try to minimize that from the design perspective. To try to minimize as many iterations between design and flight test.
So for aerospace, we all know there's a lot of branches. So what are the other different types of branches in our company just besides what you do?
So we have, I'm trying to think how many different departments. We have like 5 or 6 different departments. I am within the experimental flight test department. So this includes technicians and mechanics that actually maintain our aircraft, install modifications to our aircraft, but it also includes the flight test engineer and the flight test pilot, so both experimental. So that's what it includes. We have a design department, so it's in charge of designing new products. For example, the design department is currently working on the brand new R88 that we are working on, and the R66 NXG, which is another improvement on our current R66 line. That is what they're designed for. So they design the structural components, the console components, the landing gear, main rotor blades, all that lot. We then have a structures team. So design makes something. They may understand some of the certification basis for and strength requirements for certain materials they've done, but ultimately it's up to the structures department to not only test it, write down the report, but also like submit that to the FAA. So the structures department is in charge of the static testing, either by analytical analysis or real-world static testing, as well as fatigue testing to make sure that the parts survive that. They also are in charge of, with the help of flight test, they're in charge of what we call a flight strain survey. So it is putting strain gauges on an actual aircraft, going to fly certain maneuvers and figuring out what the loads are in real life flight. Because we can only do so, we don't know what the flight loads are going to be until we go and actually put it onto an aircraft. We can try to mimic it as much as we want. We can make our fatigue tests mimic it as much as we want, but ultimately it's what on the aircraft. We also have electrical engineering and systems integration. So they do more, rather than us designing PCB boards or circuit boards. They do some of that, but it's most of their time is how to integrate this radio, how to integrate this new display. We use a lot of Garmin products, and each Garmin product is slightly different. how to this navigation system, how do we integrate, how do we make sure that it not only mounts into a surface where the pilot can use it, the wires are all lined up, but also wires and the frequencies it runs does not interfere with any other frequency on the aircraft. So if I want to use a display, I don't want it to be all of a sudden, oh, I've lost all my navigation or I've lost my hydraulics. We want to make sure it's kind of limited with how much scope it has. So the electrical engineering and systems integration, they deal with that, but they also deal with the system safety side of making sure that given this failure, what's the damage it can cause? Can the pilot respond to it? So they're also part of the department. We have two more departments. We have a tooling department. So the tooling department makes test fixtures. So a lot of times in support of production, they go and make fixtures for welding, fixtures for how to put a door on. Like if you have empty places where a door would be, you still need to fill that empty space so we can make sure the frame will fit whatever door. So they're in charge of making these fixtures, but they're also in charge of helping us make prototype parts for various new projects that we are working on. The last bit is sustaining. So the sustaining department is kind of a one-stop shop for design, stress, and also manufacturing. So they do a lot of the making sure the production line moves forward. If there's stuff that falls out of tolerance, what we call materials MMR, I don't exactly remember what it stands for, but basically if something falls out of tolerance, they say, okay, is this an issue? Do we need to scrap this part? Can we fix the part? And kind of making sure the production line moves through, but they're also in charge of designing our legacy equipment. So 22 to 44 and 66 are considered our legacy stuff, while the 88 is our newest product. They're in charge of making either incremental improvements on our existing designs, or they're also in charge of kind of fixing stuff as they see in the field. If something happened in the field that breaks, how do we go about making that better? For example, like a mounting bolt on our engines. If that goes and breaks, how do we go and fix it? Can we make it better? If it's breaking way too often, how do we make it better? So that's kind of our different departments spread out. We also have some other departments in support of our different partners, like Rotor AI. They're making an R44 drone. There's a whole bunch of one. Like we have another one. We acquired a company back in 2024 called Cent Aerosystems. They make coaxial drones, and we also go and support them from a production standpoint. So there's a lot of different fields from the testing. If you want to go testing, if you want to do design, if you want to go and break stuff like structures. But the best part about it is what my job was to break something. Like it's rare nowadays. So like, okay, you don't want to go and break something. Like, no, that is my job. My job is to figure out how much it takes to break it, what loads it took to break it, and write a report on like how did I break it. That is a very rare thing to find out there. So there's a whole bunch of stuff within aerospace. You find your niche, whether and also there's also a niche of customer support. Like if you want to talk to customers, you're more than welcome to talk to customers. If you don't want to talk to anyone, you also don't talk to anyone. So we have a lot of different disciplines with a lot of different parts. But the great thing about Robinson is it's all in one place. It's all here in Torrance, California. It's all in one factory. We have design, structures, production, flight tests, experimental, and production all in one place. There's no other place for it, and that is a more and more rare thing nowadays as companies get more and more global. It's an unfortunate reality of just manufacturing is cheaper somewhere while design recruitment for talent is better elsewhere.
So while growing up, did you always imagine yourself working in aerospace and aviation?
Yes, I think I was going to always work in aviation. What I was going to do in aviation was not necessarily I didn't know that as a kid. Kind of worked out. It's like I mentioned before, I wanted to be a pilot when I was growing up. Ultimately, I am a helicopter pilot now, so I realized that from going through engineering. I knew that being an engineer would lead me to possibly a pilot rather than the other way around. So society kind of like also like familial pushes and urges, like they wanted me to go into engineering, so there's also that side of it. But I knew I had a knack for math and to do that kind of stuff, and being able to sit down, problem solve. So I knew engineering was the way I could go. Ultimately, combine my two passions, the talent that I had for math and problem solving, plus my passion for aviation, and that's ultimately what culminates with aerospace.
That's so cool and inspiring. Now I want to talk about what your job actually looks like. So what does a typical day at Robinson look like for you?
So typical day of Robinson is a lot of time is behind a computer. So the great part about being a flight test engineer is you are able to be in the aircraft, test the system on the aircraft with the pilot, next to you. That is about 10% of the time I do, probably even less than that. But it requires you to do 90% of that is test reports, test planning. So you need to do a lot more planning, a lot more writing on the beforehand and the afterhand than the actual testing. The testing, my testing, for example, for my most recent project took about, I would say it probably took about like 3 hours, but I've been working on that test plan for like 3 or 4 months. So it culminates in about 10 hours of testing, but it takes way more hours, hundreds of hours to actually go and get to that point where we feel safe enough to test it. We understand what we're testing, and then writing out different cards and stuff like that to support that. So a lot of times it's spent behind a computer, but a lot of times because my office is within the experimental flight test department or hangar, I walk out my door and all of our test ships are there, so I can go look into the test ships, see what test ships have, go and test, talk to the mechanics, talk to the technicians that are out there to know, okay, I want to add this, for instance, I want to add this pressure transducer to our hydraulic system to do a test on system pressure. How do I go about doing it? What are the hookup points that you suggest? What do you think is the easiest for you to do, the safest for you to do, and how do I string wires from that pressure transducer to a data acquisition unit? Those all need to be asked. I can't just be like, this is what I want to do, this is where I want to go. So I take the input of a lot of our mechanics, our technicians, our design engineers, structures engineers to best optimize for their various concerns to put it into a place that makes sense. So it's a lot of it's a lot of talking with people, which is the greatest part is collaborating with a team of people. Yes, you might be the sole engineer on certain projects, but you're not the only one that's in support of said project. You are just the figurehead, so to speak, for that.
Alright, so how do you go from identifying a problem to actually creating a solution for it?
Identifying problems, so it's a little bit, I would say it's a little bit different with aircraft certification. Usually the problem is known. So the problem is either something was happening in the field, the problem is a certification problem, the problem is a requirement that you want. So it's a little bit different than you and going and identifying the problem. The problem's already pretty much identified, or a department has already identified the problem. For example, working on a new engine, my project is working on a new engine governor. We found out that the engine governor speed sensor, the engine speed sensor was taken from the camshaft of the engine. The camshaft engine, it sometimes as the camshaft gets older and older, metallized parts start to shave off and cause erroneous data for the Hall effect sensor that's in there. So that was the problem that we found, was that we were having issues with our governors inputting the wrong command because it was getting wrong data. The new governor that we're working on not only changes that sensor from the camshaft, we're putting it onto the flywheel now, where we don't have that much of an issue for metal components causing an issue for the Hall effect. It's also on the outside. It's a lot easier to maintain, a lot easier to inspect. But this new governor now is a software and electronic hardware, but the previous one was just electronic hardware. So now we have a software base where it can recognize a bad signal and it stop itself before it makes a bad output. Previously, it was bad signal goes in, bad data goes out, regardless of what it was doing. This one now is that bad signal goes in. Oh, this data makes sense. It doesn't make sense. I'm going to turn myself off before I make a bad data output. So usually the problem is known, and that's how we go about solving the problem. Is okay. Now we make a software-based design, or we have certification basis of we need to put another alternator on the aircraft. How do we go about doing that? Where are the mounting points for it? So it's a lot of times the solution with our input is just made by design. It's made by the electrical department, system safety. We're ultimately the ones that are testing that on the aircraft itself. We are not necessarily the ones that are the sole coming up with the solution. We're the ones helping come up with the solution.
So obviously, a lot of people don't know the difference between like the different parts of the aviation, like me. So can you talk about the difference between the aerodynamics of a helicopter versus like an airplane or a rocket?
So airplanes and rockets deal with a lot more fixed conditions or static conditions, like going at this airspeed at this angle of attack. There aren't many changing maneuvers. Yes, you have banking maneuvers and yawing maneuvers, but it is a lot more predictable and a lot more stable of a condition. helicopter's conditions are all over the place. We can hover out of ground effect at 2,000 feet in the air at like 50 degrees Celsius, for example. Or we can be moving at 100 knots in level flight. We can move sideways at 100 knots, backwards at 100 knots. You can move in any direction. You can move up or down. That's the joy of being in a helicopter. Is you're not, your nose may be pointing in one direction, but you're maybe not be going that direction. So a lot of times with aerodynamics is there's no optimized airfoil profile shape. That's the same way there's an optimized shape for rockets. There's an optimized shape for fixed wing planes because there is a trim condition that you're setting it for. Helicopters have a trim condition, but that trim condition is so wildly different between the various aspects of moving side to side, up and down. But there are certain ways we can mitigate that. So we have to deal with a downwash of the main rotor blades. That's ultimately where we create lift, but a downwash hitting the cabin can cause some issues if it hypothetically circulates back into the rotor system and causes an issue, or it's hitting a flat surface, causing that flat surface to go down. So we have issues like that where it's not an issue that we have running into airplanes. For example, the vertical fins, the vertical stabilizers on the back of the helicopter, they are trimmed for a specific flight condition where if you're in level flight, it reduces the amount of tail rotor thrust that you need to compensate for the torque of the aircraft. So they are airfoil shaped, and they're airfoil shaped to correct the nose angle because, given a force, there's a reaction force. Newton's second law. There's a opposite reaction force. So because the rotor, for example, for our system, the rotor blades want to turn to the right, so the nose wants. It's counterclockwise. Our nose wants to go right. So we counteract that with a tail rotor thrust that pushes in this direction. So then it pushes it right. But in a trim condition, now you have not only the tail rotor thrust helping compensate for the anti-torque, but also you have vertical stabilizers that also help compensate for that as well. But when you're hovering, you don't have that benefit of airflow going over the vertical stabilizer. So it's only a benefit in force flight. Horizontal stabilizer. The reason for a horizontal stabilizer, it's a flipped airfoil wing. So rather than generating lift up, it's generating lift down. The reason why is to go forward in a helicopter, you want to put your nose forward. So the faster you want to go, the more you got to put your nose forward. That the horizontal stabilizer brings the nose up because it runs as you go faster and faster. There's more air going over that foil, bringing your nose up. So then you can actually see where you're going. You're not staring into the ground. So there are various aspects that aerodynamics is also very much on airfoil shape of the blades themselves. We have, rather than having a asymmetric airfoil shape like airplanes or rockets don't really have that. I think mostly airplanes have the asymmetric airfoil shape. Helicopters have a symmetrical airfoil shape for their main rotor blades because what we're doing is we can change the pitch of the blades. That's how we generate more lift. By making it symmetrical, it's more predictable in various aspects. While with a plane is we always want to go up. It's a fixed thing. We're changing the entire aircraft to be able to create more lift or less lift. While for us, is we want a symmetrical system because we want to be able to turn it up or down and have the same predictable behavior aerodynamically.
So lastly, where do you see yourself in the next few years?
I see myself still continuing with Robinson as a flight test engineer. I've only done about 6 months in this new position, so there's a lot more learning I need to do, a lot more learning from my mentors and stuff like that. So, but there's also a lot more work ahead of us. Most of my work currently in flight test engineering has been working on our current existing products, current product lines, but with the 88 just around the door and currently going through a design phase, at some point that's going to end up in flight tests, and ultimately we will need to go with flight test vehicle number 1. We will need to go and actually go do flight testing. Go and this will be from the ground up, brand new charts, brand new performance charts, brand new characteristics that we may or may not understand, brand new systems to be testing. So we'll have our work cut out for us for the next coming years, at least until the end of the decade, when we hope our 88 certification will finish and production will start sending out to customers. So that's where I see myself in the next coming years at Robinson is to, I'll stay until 88 certification. We'll see after that, but that's already 5-6 years already planned out. Is hoping to stay at Robinson to further my knowledge in flight testing and learning from the various people that work there.
This has been a really insightful conversation. Hearing about your path, your flying experiences, and your work as an engineer has not only inspired me, but it also helped me learn like more about what you do. And like you talked about failure, like if I fail, then I need to work on how to like gain from that, because failure is part of life. And I really appreciate you coming here. Thank you so much for coming here. And I know the viewers and listeners will also gain from your perspective. So thank you so much.
Thank you for inviting me. It was a great experience to learn from your perspective as well. I hope it was helpful for other people.
I hope we can stay in touch and maybe have an interview again in the future.
Definitely.
Thank you so much. Thank you to everyone who joined us for the first podcast. I hope you all learned something new and got inspired just like I did. Make sure to join me next time for another conversation that inspires curiosity and learning. Till then, explore, engineer, and elevate. See you next time.